are watching the evolution of a galaxy, an event no man will ever see. But computer animation gives cosmic theories shape and dimension. This spiral model stands for the more than 1 billion galaxies that populate the universe. Its origin stretches back billions of years to a time when our entire solar system was only a cloud of gas and dust. Although galaxies are the largest single collection of stars in the universe, they are as basic to cosmology as atoms to physics. Among galaxies, astronomers search for the horizon, if there is one, to the universe. It is not easy to find good sites for observatories. Only a few places on Earth have the right seeing conditions. It was in the late 50s that a party of astronomers and surveyors searching for such a site made its way over uninhabited areas of the Andes in Chile. They knew what they were looking for. It had to be far from the light pollution and smog of cities. It had to be at least 2,000 meters high, beyond the range of temperature inversions. It had to have calm air and clear nights. A team of astronomers from AURA, the Association of Universities for Research in Astronomy, and the University of Chile surveyed many mountaintops. Finally, after 3.5 years of astronomical observations and testing, they found what is one of the best places on Earth for observing the stars, Cerro Tololo. Here, the North American universities that comprise AURA and the University of Chile cooperated in building the first large observatory in South America, Cerro Tololo Inter-American Observatory. The southern sky is very special to astronomers, for there they can see regions of the universe invisible to northern observatories. Here, the nearest visible galaxy is 10 times closer than the nearest visible galaxy from the north. It is the most favorable spot for observing Mars and some other planets as they make their closest approaches to Earth. Only in the southern hemisphere can astronomers favorably look toward the hub of our home galaxy, the Milky Way. For the best views of stars and galaxies, astronomers of many countries come to Cerro Tololo. Dr. Joachim Dox of Ruhr University in Bochum, Germany, comes here to study clusters of stars in the Milky Way.
There are two reasons for doing this work here. First, the wonderful weather in South America, in Chile, which we don't have in Europe. And the second reason is the southern skies, which show us the brightest parts of our galaxy, which we can't see from the northern hemisphere.
For Argentine astronomers, Dr. Roberto Cistero and his wife, Dr. Marta Castore de Cistero, Cerro Tololo is the best place to study double stars, stars that travel in pairs. Astronomers, like the rest of us, see only white light when they look at stars. But with sophisticated tools, such as those at Cerro Tololo, it is possible to measure and analyze light. Such elaborate detective work is necessary, for light is the calling card of the cosmos. Less than 100 years ago, talk of the cosmos was reserved to metaphysics. Most of what we know about the galaxies has been discovered during this century. Until the early 1900s, most people thought the Milky Way was the entire universe and that our solar system was the center of it. Around 1916, American astronomer Harlow Shapley put an end to that illusion and did for our galaxy what Copernicus had done for the solar system. His measurements proved we are nowhere near the center of the Milky Way, but far out in its suburbs, some 33,000 light years away. Shapley estimated the size of our thin, pancake-shaped galaxy about 100,000 light years across. The enormity of the star system we inhabit became a stunning reality. California astronomer Edwin Hubble took us beyond our galaxy and opened the great frontier of cosmology. In the early 1920s, he established the existence of vast star systems like the Milky Way, situated 1 million or more light years outside our galaxy. The curtain was raised on a universe of dazzling dimensions. As Hubble and his colleague Milton Humason analyzed their data, they made another discovery. The more distant the galaxy, the faster it travels away from us. This observation suggested the theory of an expanding universe, one populated by billions of galaxies, all separated by vast regions of space, some traveling at close to the speed of light. Hubble classified galaxies according to shape. Most commonly observed are spirals containing both old and new stars. Within the spiral arms, stars are continually being born. Also common are barred spirals, characterized by a bar across the center and long trailing arms. Elliptical galaxies contain old stars. In these galaxies, star birth has apparently ceased. The old stars remain in a halo surrounding the nucleus. Irregular galaxies are believed to be among the youngest in the universe. This is the largest of two Magellanic Clouds, our nearest neighboring galaxies, observable only from the southern hemisphere. Because they are closest to us, only about 180,000 light years away, the Magellanic Clouds offer greater opportunities for studying the details of galaxies than are available in the northern skies. From Cerro Tololo, astronomers can see with a 20-inch telescope as much detail in these galaxies as can be seen in the nearest spiral galaxy visible from the north with an instrument 10 times larger. In spite of the southern hemisphere's observational advantages, most of the world's observatories are clustered north of the equator, where most of the world's population flourishes. At places such as Kitt Peak National Observatory in Tucson, Arizona, astronomers have spent years measuring and mapping the northern sky. But already skies over many of the largest telescopes are obscured by smog, lights, and other products of industrial society. Large southern observatories are few by comparison: Australia, South Africa, Argentina, and now Chile. Already the 6 telescopes on Cerro Tololo and the telescopes of its new neighbor, the European Southern Observatory, are in great demand by astronomers eager to make up for lost time. Since its invention, the telescope has been a light-gathering instrument. It is still basically that, but the demands of modern astronomers for more information have led to complex instruments which equip the telescope not only to collect light, but also to analyze it. During the day, highly skilled technicians prepare the telescope for nighttime observations. Attachments such as the photometer, which measures a star's brightness, are installed. Dry ice is put into a cold box to increase the sensitivity of electronic cells that measure starlight. Dr. Victor Blanco, director of Cerro Tololo, has the task of scheduling observing time on the instruments, which are booked many months in advance. Dr. Bart Bach, a world-renowned authority on the structure of our galaxy, comes to Chile to continue his studies of the Milky Way. Cerro Tololo's stable air offers him the best seeing conditions. Tonight, Dr. Bach will look for young stars in the Milky Way. He will use the Schmidt telescope, a gigantic wide-angle camera designed to take pictures of distant stars. His assistant observer, Senor Gaston Araya, prepares a photographic plate made of glass and places it inside the camera.
Primäre región, 11 horas y 30 minutos, menos 61 grados, por favor. Muy bien, doctor.
Dr. Bach tells Gaston at which region of the sky to aim the telescope. Positioning a telescope depends on two coordinates, an angle on the east-west arc across the sky, which astronomers call the hour angle, and an angle along the north-south axis of the Earth, known as the angle of declination. Once the telescope has been set, Gaston checks the position in the Milky Way field, which Dr. Bach wants to photograph. He opens the shutter, exposing the plate to the faint starlight. Exposure time varies from 15 minutes to several hours, depending on the star's brightness. The next day, Dr. Bach examines the plates which were taken from the Schmidt. Using a binocular microscope, he compares them, looking for young blue stars. To Dr. Bach, these young stars are like street lights which help mark the spiral arms in our galaxy. Once he has used the Schmidt photographs to locate the young stars, Dr. Bach now needs precise measurements of their brightness and color. To obtain this information, he sets out late in the afternoon for another long night's work. After many years of observing, Dr. Bach has developed a special feeling for his profession.
That there are all sorts of astronomers. I happen to be the type who starts with looking and wanting to understand. There are others, and some of our most powerful ones today are people who are basically physicists and mathematicians. And then they say, I know a lot of physics and mathematics. Where can I apply it? And they find that the labs aren't big enough, that the generators aren't powerful enough, that the atom smashers don't half of the job. And they say, Lord Almighty, look, there is the whole universe waiting for us, full of physical experiments going on.
Aquí es la carta astronómica por la noche.
On a finding chart, Dr. Bach shows another assistant, Senor Arturo Gomez, the area of the Milky Way he wants to observe. From a console, Arturo moves the 60-inch telescope into position. The seeing conditions are so favorable on Cerro Tololo that Dr. Bach will be able to observe regions that would require a telescope almost 3 times larger at most northern observatories. He spends up to 11 hours of intense concentration tracking the stars. His observations take him far from the human timescale.
When we see a star, like for example the Alpha Centauri, that is 4 light years away. We see the messages from that star 4 years after they leave the star. If we look at the center of the Milky Way or regions near there, 33,000 light years is the distance. That means the messages take 33,000 years to travel across to us. If we look at the star in the Andromeda Galaxy, that's 2 million light years away or a little more, then we see that star as it was 2 million years ago. In other words, astronomers who look in space look not only at very great distances, but they look back into time.
To measure light from the past, Dr. Buck uses a photometer, a sensitive photocell attached to the telescope. Like a light meter, the photometer records the brightness of stars. These signals appear as lines on a chart recording. The brighter the star, the more current recorded, and the longer the line. These 11 rolls represent 11 nights' work. Now the information must be analyzed and interpreted, a job that takes more time than the observations. Dr. Priscilla Bach, who entered astronomy through mathematics, checks the data. Comparing recorded signals, she calculates the brightness of each star. Searching among our galaxy's 200 billion stars, the Bachs have found many which mark its spiral arms. Photometry, the measurement of brightness, is one of astronomy's workhorses. Another is spectroscopy, a method of separating starlight into its various wavelengths and photographing the resulting spectrum. This is a photograph of a star field. This is a spectrogram of the same star field. Dr. Patrick Osmer, staff astronomer at Cerro Tololo, checks the 60-inch telescope he will use in taking a spectrogram of an individual star. To do this, he goes one floor below to an insulated room constructed to hold the spectrograph, which is too large to be attached directly to the moving telescope. Dr. Osmer lines up the star whose spectrum he wants to photograph. An adjacent black room contains the spectrograph and a 6-foot-long camera. Starlight entering the telescope above is reflected by a system of mirrors to a grating that breaks up white light into its component colors. Instead of regular film, a special glass plate is used. Just as a camera must be light tight in order to take a picture, so the room must be completely dark while Dr. Osmer takes the spectrogram. The telescope concentrates the light of the star at the point of focus, where a narrow slit is placed. The width of the slit can be adjusted from 1/1000th of an inch to a maximum of 1/16th of an inch. Its length can also be adjusted. The narrower the slit, the greater the resolving power. Through the eyepiece, he can see a magnified view of the star on the slit. The shutter exposes the film. Exposure time varies from a few minutes to several hours or even several nights, depending on the faintness of the star. Closing the shutter, Dr. Osmer completes his spectral picture. Later, he examines the developed plate. The spectrogram is no ordinary picture. Encoded in its tiny lines is more information about a star than one can obtain by any other method. By analyzing the patterns of the lines, Dr. Osmer learns the star's chemical composition, its temperature and atmospheric pressure. He can determine the speed at which it rotates, its velocity, and whether it is moving toward or away from the Earth. Spectroscopy, photometry, photography. These 3 methods of observation all help astronomers to plot the life expectancies of stars. For they too are born, grow old, and die. In our galaxy, there are stars of all ages, sizes, and types. This photograph shows a dark, cone-shaped area, a cosmic bag of gas and dust, which astronomers suspect is a maternity ward of stars. How are stars formed? Hydrogen and dust are the basic ingredients. As condensations form, the force of gravity attracts more particles. This action is multiplied 1 billion times in forming the nucleus of a star. For several million years, the nucleus attracts more particles, expanding, compacting. Heat is generated by the force of gravity and the crush of particles. As the embryonic star contracts, it gets hotter and hotter, radiates more light. Finally, after a few million years, it becomes visible to man and is called a protostar. Though not yet of age, the star can now be plotted on a chart as familiar to astronomers as their ABCs, the Hertzsprung-Russell diagram. It was in the early 1900s that Danish astronomer Einar Hertzsprung and American astronomer Henry Norris Russell discovered that stars fall into certain patterns according to their brightness and color. Color indicates temperature. A red star is cool. A blue star is hot. By substituting our sun for the protostar, we can follow its life cycle on the HR diagram. Deep inside the protostar, pressures mount. Temperatures rise. Suddenly, hydrogen in the core ignites, and in the violence of nuclear fusion, our sun is born. It is on what is called the main sequence now, and will remain there for millions of years. It is known as a G-type star. Its age is 4.5 billion years. As the sun's surface boils from hydrogen burning, it increases in brightness. The sun's composition is changing now. Hydrogen is converting to helium. The diameter is increasing. Temperatures decreasing. 80 million years after leaving the main sequence, the sun changes violently. It expands 200 times, engulfs Mercury, Venus, and our Earth. The helium ignites. Astronomers call it the helium flash. With the change of fuel, weird things happen. The sun becomes unstable. Pressures expand it. Gravity contracts it. It pulsates and is called a variable star. There are many other types of variables. Some pulsate once a year, others in a few seconds. Having passed through the variable stage, the sun becomes brighter, 10,000 times brighter than our present sun. Expands 300 times larger. It has reached its maximum size and is called a red giant. As the supply of helium diminishes, the sun contracts. Deep inside, the crush of gravity changes the structure of atoms. Heavy elements are formed, then ignite. Now temperatures soar, reach well beyond 1 billion degrees. Decreasing in size and in brightness, the sun enters its last phase. It becomes white and small, only 1/100th the size of our present sun. And now, this white dwarf begins the long, slow process of burning out. Invisible, it will wander through space. The only energy remaining is that which formed it, gravity. At Cerro Tololo, Dr. Sidney Vanderberg of the University of Toronto will use the HR diagram to investigate a cluster of stars. In what time span did the stars evolve? How old is the cluster? Is it the approximate age of nearby clusters? If so, could this indicate the age of this small region of the Milky Way? But first, the observations. Later, an assistant plots the diagram. Stars are the living record of the universe. Just as rocks provide clues to the Earth's beginning, so the stars are clues to the past and future of galaxies, including our own. How old is our universe? Is it finite or infinite? How did galaxies originate? Are the galaxies winding or unwinding? Does the universe have an edge? Will the expanding universe ever contract? Working at observatories like Cerro Tololo, astronomers spend most of their lives pursuing questions that dwarf our concepts of space and time. If anyone wonders why, Dr. Bart Bach has an answer.
When I sit at my telescope at night and start working, and things get completely dark, and then there is the sky above, and then you have a feeling that you want to know, you want to understand. Well, what we get in astronomy, is the opportunity to understand and to know, to search for the ultimate truth of beginnings. I look at objects that have not been seen nor photographed before. This is a great reward, to be the first one to do certain things and to do them reasonably well, and to be given by society the power to do these things well. There are many reasons why astronomers like to do the work that they are doing. But one of the principal ones is that we love the beauty of the universe with which we are privileged to work. The French astronomer, mathematician Poincaré once said, "L'astronomie est utile parce qu'elle est belle." Astronomy is useful because it is beautiful. Some people say that astronomers, by probing into the depths of the universe, destroy the feeling of beauty, the feeling of majesty that we get when we look at the heavens. I think it's just the other way around. By our probing, we reveal new beauty. We reveal new mystery. We reveal something that touches the soul. We really want to see the universe in all its beauty. To do so, we need our instruments. We need our telescopes, and we see something new and great in our universe that no one has dreamt of before.
Produced by the Association of Universities for Research in Astronomy, under contract with the National Science Foundation.